Before we look at our log laws, we have to ask ourselves, what is a logarithm? If we write out an example, let's say log to the base 2 of 8, we will read this as log of 8 to the base 2, or log to the base 2 of 8. It's basically asking, what power must I raise 2 by to equal 8? Alright, so what power do I raise the 2 by to equal 8? So I could write that as 2 to some unknown power equals 8. Or, alternatively, using algebra, we could say 2 to the power of x equals 8. So we could say, therefore, x is equal to log to the base 2 of 8. In this example, 2 to the power of 3 would equal 8, so that whole thing would equal 3. There will be times where you won't get a nice whole number. You might have to round off to decimal places, or you could leave it in log form for your exact value. So, for example, if you had 2 to the power of x equals 10, we know that 2 cubed would be 8, and 2 to the power of 4 would be 16. However, we don't have a nice even number that we can raise 2 by to equal 10. So we'd just write our final answer in exact form would be log to the base 2 of 10. Now we've looked at what logs are, let's look at shortcuts we can use just like our index laws. And we wrote 2 to the power of 3 times 2 to the power of 5. We looked at expanded notation, all these different reasons, but we finally realized the shortcut is just to add the powers together. And we'd get 2 to the power of 8. We had all the other ones, so if we were dividing 2 to the power of 5 divided by 2 to the power of 3, for example, we just subtract the powers. If we look closely at our first two log laws, we can see the relationship here is when we're multiplying the same base, we add the powers. You can see here the logs and the log laws, we've got the same bases. Alright, we're adding the logs together, so when they're inside the one log, it's multiplying. You can see here, adding goes with multiplying. Dividing goes with subtracting the powers. So when it's one log with a fraction inside it, or two terms or expressions divided by each other, we can separate that into two logs with a minus in between. So look at the difference between them. Similarly, the rest of the log laws match up with their index laws. So let's say 2 to the power of 3 all to the power of 5 would be 2 to the power of 3 times 5. We can actually put the powers inside, so the multiplying by p actually goes inside as a power of p. When we have a negative root here, we can take that negative out, which closely relates to log law 3. And log law 5 is basically just saying we know anything to the power of 0 is going to equal 1. So when we look at log a of 1, saying what power do I have to raise a by to equal 1, anything to the power of 0 is going to be 1. So it doesn't matter what the base is. I could have log to the base 17 of 1, I could have log to the base 3 of 1, I could have log to the base, I don't know, 219 to the 1. They're all going to equal 0. Because anything, any base to the power of 0 will equal 1. Let's look at solving equations using logarithms. To start off, we'll simplify a couple of expressions. So this first one here, we've got log to the base 4 of 1 over 64. What we should do is try and write what's inside the brackets in terms of 4 to the power of something. So we should recognize that 64 is the same as 4 to the power of 3, or 4 cubed. So this whole expression could be written as log to the base 4 of 1 over 4 cubed. Once we get to here, we can then write 1 over 4 cubed as 4 to the power of negative 3. So log to the base 4 of 4 to the power of negative 3. Now, what a log is asking us is, what power must the base, which in this case is 4, be raised to equal everything inside this bracket here? So, well, we've already got a base of 4, so to raise 4 to the power of negative 3 would give us what's inside the brackets. So this whole expression just equals negative 3. Let's look a little bit more complex. Let's look at a more complex example. We've got x, we have x times log of 8 to the base 2 plus log of 8 to the power of 1 minus x to the base 2. The good news is we can see we've got the same bases in our logs. So let's move everything outside those logs. So for example, this x, let's put that inside. We can use that. We can do that by writing that as log to the base 2 of 8 to the power of x plus log to the base 2 of 8 to the power of 1 minus x. Now from our log laws, just like in our index laws, if we've got a plus in the middle here, we can write this as log to the base 2, and we combine these two logs because they're the same base, and we can write that as 8 to the power of x multiplied by 8 to the power of 1 minus x. Going further, we can see that now we have 8 to the power of x times 8 to the power of 1 minus x, which both have a base of 8, so we can combine those powers by adding them together, which would give us log to the base 2 of 8 to the power of x plus 1 minus x. From here, we can see x minus x is 0, so we'd be left with log to the base 2 of 8 to the power of 1. So we're saying what power must 2 be raised to equal 8? We know that 2 cubed is 8, so our answer is just 3. Moving on to an equation now. This one looks a lot more complex. We have log to the base 10 of x squared minus 2x plus 8 equals to 2 times log to the base 10 of x. What we should do first is try and represent both sides of the equation as just logs to the same base. So we're going to try and get everything outside. So for example, this 2, we're going to put inside there as a power of 2. So now we'd get log to the base 10 of this quadratic x squared minus 2x plus 8 equals log to the base 10 of x squared. Once we have logs to the same base on both sides, nothing else around them, we can cancel these logs off. So x squared minus 2x plus 8 is equal to x squared. Now moving the x to the other side, take away x squared from both sides, would end up cancelling these two off. So we get minus 2x plus 8 equals to 0. And let's solve for x. Let's move the 2x across, plusing 2x to both sides. So 2x equals 8. Divide both sides by 2. We'd get x equals to 4.